Okay, so we're looking at the basic definitions of potential difference, current and resistance to begin with, and then we'll have a quick look at the experiments, the Van de Graaff experiments as well. Right, so potential difference, okay, current and resistance. You know from junior cert, these are all the important ones. Now, what they mean? Potential difference is the energy. It's the energy needed to move 1 coulomb of charge, unit charge, move 1 coulomb of charge from one place to the other. Now let's go back to potential energy and remind ourselves what's going on. So I have a book here, okay, and I have 3 books, or a series of books here on this bookshelf. Okay, so if I put this book here, it requires energy. I must do work to move that book up to there. Okay, I must do work. There's work done in moving the book up to there. Okay, that has now gained potential energy. Okay, so there's work done, and the work done is equal to potential energy gained. It's exactly the same as what we deal with in dividing the voltage. Okay, so the voltage is the work done or the energy gained, but we generate it down as W. So the work done in moving unit charge, okay, so per charge from one point to the other. So in other words, if I just draw the two of these, okay, A and B, okay, the work done in moving a charge from here to here is equal to the potential difference. Okay, and it's the energy gained if you're going in the opposite direction, right? This is where the electron volt comes from, because it's the work done in moving 1 coulomb of charge across 1 volt, and that's the electron volt. Okay, we'll have a look at that in the notes later. Okay, second thing is current. Okay, and current is just how much charge flows per second in a certain time. We'll go with seconds. So it's the charge flowing per unit time per second. Okay, simple as that. And we're not going to go into detail on resistance. You remember from junior cert, from Ohm's law. We'll be doing this in current and electricity a lot. Okay, it's just the ratio of the two of these. So R is V divided by I, and that's the 3 of them. Okay, this is the most technical one. Okay, work done in moving unit charge. So work done divided by charge. Current, charge per unit time. So charge divided by the time. And then resistance is the ratio of the two. Okay, just very briefly, let's look at the idea of the electron volt. Okay, very important. Okay, so we have a potential difference of 1 volt, and the charge is equal to the charge in the electron E. So the voltage is work done divided by charge. Okay, so it is the work done is Q by V. Okay, and if it's 1 electron and it's 1 volt, okay, the work done is E by 1. So the work done is the charge on the electron, 1.6 by 10 to the minus 19 coulombs. Okay, so that's it. Right. Second thing we're going to look at is the 3 experiments that we need to know on the Van de Graaff generator. Okay. Now we don't need to go into detail on the Van de Graaff generator. Okay, and we've had a look at the gold leaf electroscope, so we've seen that in the notes and we know how it works. Okay, so let's look at the 3 core experiments that you're supposed to be able to do. Okay, the first one, right, is right, to show that charge resides in the outside of a conductor. So in each case, we have a charged Van de Graaff generator. Okay, in this case, we have a metal conductor, a can, okay, and charge resides in the outside. Effectively, think about it, because charge repel, they keep repelling until they're as far away from each other as possible, which will be on the outside of the surface. There is no charge in here, there is no charge in there. So this is, there has no charge. So how do we show this? We use our proof plane. Now remember, a proof plane is just a metal disc with an insulated handle. And all that does is it carries charge from our experiment to our detector. And in this case, our detector is, we're going to use a coulomb meter. Okay, in your notes, we talk about gold leaf electroscope, either will do. Okay, so we're going to move the charge. So all you do is you bring a proof plane close to the point you're interested in, and then bring it close to your coulomb meter, and we see. Okay, so I'm going to just call that C with a circle, the coulomb meter. Okay, and what we do is we check the charge on the outside, and the coulomb meter will register a charge. We earth this so it will remove any charge from it, and we do it again for inside, and there should be no charge. Okay, there should be no charge inside. This is why a car is a good place to be in during a lightning storm, because your car is effectively a metal box and charge resides in the outside of the car. Okay, so that's that one. Now the second experiment is to show that the charge distribution on a pear-shaped conductor. So on top of this again, we have our charge Van de Graaff generator and we have a pear-shaped conductor. Now there's a conductor that looks like a pear. And what you find is there's charge throughout the conductor, but it is concentrated here at the points. Okay, so what we do again is with the proof plane, we bring the proof plane to here, to coulometer, and we bring the proof plane to here, to coulometer, and the pointed end should have more charge. Okay, that's it. And the third experiment takes that one step further, in that we have a point-shaped conductor, we have a point on the top. Okay, now what happens here is, we're going to look at why this happens as well. A huge amount of plus charge forms in the point because it's a very, very small area. Okay, and what happens is the air around this charge, this has got a very large electric field. Okay, so the air around it, there's large forces and the air gets ionized, it's turned to plus or minus charges. Okay, so the air turns into plus or minus charges, that's very important, the air is ionized. And what happens is the plus charges are repelled, okay, and the minus charges are attracted. Now the minus charges that are attracted, okay, right, so that's what happens, sorry, the actual experiment. The minus charges and the plus charges are being repelled act as a wind, okay, and you put a candle up here, okay, and the candle blows. Okay, and if you put your hand up to it, you'll feel it, okay, you'll feel it. You won't feel it on the video, but you'll feel it when you do it in 4C. Okay, right. What is happening then, okay, and I'm kind of explaining the experiment while I'm also doing it. What is happening is the air is ionized, the plus charges are repelled, that's what causes the wind, the minus charges are attracted, and they neutralize the plus charges on the point, so they neutralize the point. So what's effectively happening is plus charge is being taken off the dome and it's being sent out into the air. Okay, because think the plus charges are being lost from the dome and plus charges are being repelled. They're not the same plus charges, but you can think of it as the same plus charges. So it's leaking charge. We'll see when we do the experiment. I'll try to get a spark on my finger, okay, and the spark on the finger will be very small, which will indicate that the charge on the dome is much less than it was without the point. Okay, that's it. They're the experiments in the Van de Graaff. Let's have a look at them and we'll move on from there tomorrow. Thanks a million. Bye bye.